So I wanted to clarify what, um, how to interpret the chi-squared table. So we've already calculated our chi-squared value, which was that whole observed minus expected squared over expected sum thing. And we have calculated the degrees of freedom. So now we have this table of critical values. So all of the things in white, all the cells in white are chi-squared values. They're not p-values. And um, every row is represented by a different degree of freedom. So this table has the first 12 degrees of freedom. Um, and then in the columns, we have p-values. So p-values in general, when you're interpreting p-values in statistics, p-values are the probability of seeing the data that you actually saw if the null hypothesis is true, right? So if we want a p-value of 0.05, we are saying that we're willing to tolerate a 5% rejection of the null hypothesis, even though the null hypothesis is true, okay? So this is basically saying what percentage of the time we're willing to accept being wrong, okay? So the 0.05 is just an arbitrary cutoff that the scientific community uses to draw the line, right? You could imagine in some alternate universe we decided to use 0.01, and in fact, in some particular scientific enterprises, we don't tolerate an error rate of 5%, right? We don't tolerate that 5% of the time we could see this data just by chance. We would tolerate much smaller p-values. Okay. That said, unless otherwise stated, assume that the type 1 error that we're willing to accept is 0.05. So we have our chi-squared value, and essentially what the table is saying is that with 1 degree of freedom at a p-value of 0.05, the chi-squared value associated with that p-value is 3.84. Okay? So any chi-squared value greater than or equal to 3.84 means that we would have to reject the null hypothesis. So another way of saying that is, let's say that we've calculated the chi-squared value based on our data, right? So we see the number of individuals in each genotypic class, right? So many are big A, so many are big A, little a, and another group are little a, little a. We calculate the chi-squared value. We calculate degrees of freedom as 1, and we get a chi-squared value of 3.84. 3.84 tells us that we would see those numbers belonging to each of those genotypic classes 5% of the time if the null hypothesis is true. And remember, for Hardy-Weinberg, the null hypothesis is the population is in Hardy-Weinberg equilibrium, right? There's no evolutionary change going on in the population, right? All of those assumptions have been met, okay? So if the chi-squared value were 3.84, then we would reject the null hypothesis, right? That would be the smallest value, smallest chi-squared value that would cause us to reject the null hypothesis. So if we have anything greater than 3.84 with 1 degree of freedom, we would also reject the null hypothesis, right? And if we wanted to be very specific about it, let's say we had a chi-squared value of 10.83 and not a chi-squared value of 3.84, okay? That means that with a chi-square value of 10.83, the probability of those number of individuals in each of those genotypic classes of seeing those numbers when the population is in Hardy-Weinberg equilibrium is 0.001, right? So it's even less likely that we would see those data given that the population is in Hardy-Weinberg, which means it's probably less likely that the population is in Hardy-Weinberg, right? So the higher the chi-squared value, the less and less likely that those data are to be generated if a population is in Hardy-Weinberg equilibrium.